Today you will multiply and divide radical expressions. If you have the nth root of a and the nth root of b, and these are real numbers, then the nth root of a times the nth root of b is the nth root of a times b. So if we look at our example there, the square root of 2 times the square root of 3, because they have the same root, they're both square root, we can do 2 times 3 and say the square root of 6. However, if I have the 10th root or the 4th root of 10 and the square root of 5, because they aren't the same type of root, we cannot multiply those because the indexes are different. The 4th root has an index of 4 and the square root has an index of 2. So in our first example, we're going to simplify each product if it is possible. So if I have the 4th root of 125 and the 4th root of 405, and I know this is a non-calculator formative, the first thing I'm going to do is I'm going to say 125 times 405. And I am not going to waste my time and energy multiplying those two numbers together. I'm just going to go straight to a factor tree. I know if it ends in 5, I can divide by 5. And I know 5 goes into 125 25 times. 25 breaks into 5 and 5. And remember, I like to cross out numbers I've already broken down so I don't get confused later. 405, if it ends in 5, I can divide by 5. And that ends up being 81. 81 is 9 and 9, 3 and 3. That's a 9. And again, I like to cross out things I've already broken down so I don't get confused. So the next step is, remember, if I have a 4th root here, that means I want sets of 4. So notice we have 4 5s and 4 3s. So I have a 5 that comes out of the radical and a 3. So our final answer is 15. And that's it. Let's look at b. Notice we have the cube root of 12 times the square root of 7. Now, notice here that we don't have the same root, right? I can't multiply a cube root with the square root. So we just say can't multiply because the indexes are different. I want you to take a minute or two and try the 2 example U-tries. Hopefully you found for A, you cannot multiply it because I have a 4th root times a 5th root. In letter B, we just have the 5th root of 10. Our next definition is simplest form, and this is pretty self-explanatory. So when the radical is reduced as much as possible. So notice we have a simple example there for the square root of 24. Okay, now we know that we're going to do a factor tree. I know that 4 times 6 is 24. And 4 breaks into 2 and 2, 6 breaks into 2 and 3. Because I have square root, I want sets of 2. Notice a 2 comes out of the radical, and what's left inside is a 2 times 3, which would be 6. So the square root of 24 is in simplest form when we write it as 2 square root 6. So now we're going to write the simplest form of each radical again. Okay, so if I have the cube root of 135x to the 5th, okay, remember if it ends in 5, I can divide by 5. 5 goes into 135 27 times. And 27 breaks down to 3 and 9. 9 breaks down to 3 and 3. Now remember, I look at my index here, and I'm going to cross out ones I've already broken down. I want sets of 3. So notice we have 3 3s here. And we have a 5 that stays inside. Now for x to the 5th, I'm thinking in my brain, x to the 5th is like x times x times x times x times x. And if I want sets of 3, we have 1 set of 3 and 5. So an x will come out of the cube root sign, and 2 remain inside. And remember, when we have an odd root, we don't need to look for absolute values. So this would be our final answer, 3x cubed root of 5x squared. if we look at b, it does look a little bit more complex. I would probably start off by writing it as the square root of 48 times 50, because remember, odds are this first formative is no calculator at all. X to the 5th times x to the 2nd is x to the 7th. And y squared times y to the 4th is y to the 6th. Okay, and we're going to break down 48. We know that's 16 and 3, and 4 and 4. And we have a pair of 4s. 50 is 2 and 25, and 5 and 5. Right? I can cross out the ones I've already broken down. Okay, so when we simplify this, notice we have a 4 and a 5 that come out. And inside, we have a 3 times 2, because those are the numbers that don't have a partner. Now for x to the 7th, I have to think of how many sets of 2 are in 7. Well, we have 3 sets of 2 with 1 left over. And how many sets of 2 are in y to the 6th? Well, we have 3. Now, do you see how you have an even power and an even power? And when you have an even power and you take an even root, and now the power of that variable is odd, you have to have those absolute value signs. So we need absolute value signs around the y. Okay, and the reason why we don't need absolute value signs over the x, again, because when I combine x to the 5th with x squared, we know that it's not even together. So if I do an even root of an odd power that is still odd, it's not going to make a difference. And our final answer, 20x cubed, absolute value of y cubed, square root of 6x. I want you to take a minute or two and try the example you chose. Okay, so hopefully you found for A, x squared cubed root of 127x, and for B, 15x cubed, y cubed, square root 7y. Now, you may be asking yourself, well, why didn't we put absolute value signs around x? Because x to the 6th goes from an even power to an odd with an even root. Well, because in our original, x to the 5th is an odd, and x to the 1st is an odd, right? I'm not going to be able to take a negative square root. So we already know that absolute value signs is not necessary in that case. So let's talk about dividing. Combining radical expressions with quotients. If you have the nth root of a and the nth root of b, and these are real numbers where b is not equal to 0, then the nth root of a over the nth root of b is the nth root of a over b. For example, that top problem, I can write it as a giant square root sign of 5 over 8, which, remember, because it's the same root, I can write it as a square root sign if I want to. However, we don't like radicals in the bottom of a fraction, so instead of doing it that way, we are going to rationalize it. So remember to do so, we multiply top and bottom by the square root of 8. So the numerator becomes the square root of 40, and the denominator becomes 8. The square root of 40, if you were to do a factor tree and break it down, that's 4 times 10, which is 2 and 2. 10 is only going to break down to 5 and 2. So this would be 2 square root 10 over 8, which is the square root 10 over 4. The same thing is true for the bottom example. I can write it as the cube root of 2 over 16, because if I recognize they're both even numbers, I can more than likely reduce that fraction. This becomes the cube root of 1/8, which the cube root of 1 is 1, and the cube root of 8 is 2. So this brings us to our next type of problem. We're going to simplify each radical expression, So the first thing I'm going to do is I'm going to write a giant square root sign, and I'm going to put 20x to the 6th over 5x to the 4th. And I'm going to reduce that fraction. We know 5 and a 20 is 4, and x to the 6th over x to the 4th is x squared. We know the square root of 4 is 2, and the square root of x squared is now x. But remember, in our original, we had an even with an even that is now even. I have to have absolute value signs over the x because you go from an even power with an even root to an odd. Let's look at B. Letter B, we're going to approach this problem the same way. We're going to write it as a giant cube root sign, 189 x to the 7th over the 7x squared. We know 7 goes into 189 27 times. And we know x to the 7th over x squared is x to the 5th. The cube root of 27 we know to be 3. In sets of 3 there are in 5. There's 1 with 2 left over. So our final answer is 3x times the cube root of x squared. And that's it. Take a minute or two and try the example you tried. Hopefully you found this to be 5 absolute value of x. Next definition is rationalizing the denominator of a fraction. This is the process of rewriting the expression so there are no radicals in the denominator. And we kind of have already talked about this. Remember, we don't like square root in the bottom of a fraction, so you're just going to multiply whatever's in that denominator by that root on top and bottom so that it is a perfect root. This ends up being the square root of 2 over 2. In our next type of problem, we're going to rationalize each denominator of the expression. So if we look at letter A, notice we have the square root of 8x in the denominator of our fraction. So in order to make that a perfect square, I'm going to multiply the top and bottom by the square root of 8x. Our numerator is now the square root of 40x, and our denominator is just 8x. Okay? So I have to think in my mind off to the side. If I were to do a factor tree, we know 4 and 10 gives us 40. 4 breaks down to 2's, and 10 just breaks down to 2 and 5. So I'm not going to break it down. I'm going to have to multiply anyway. So the numerator becomes 2 square root 10x, and the denominator is still 8x. Now, the only thing that we can reduce is the 2 and the 8. I cannot simplify the x's because the 10x is under a radical sign. So our final answer is square root 10x over 4x. The end. Now B is a little trickier. Okay, so I would probably, because we have a cube root and we have one fraction, I would probably reduce it as much as I possibly can. So I know this is going to be the cube root of x to the 4th over 8yz cubed, because 4 over 32 reduces to 1/8. And I also know that it's like the cube root of x to the 4th. And if I look at that denominator, notice 8 is under a cube root, which means it's a perfect cube. So a 2 can come out, and inside is, we also have a z, we also have a z cubed, which is a perfect cube. So a z can also come out of that denominator. So that means inside we just have a cube root of y. Now remember, in order for that cube root to not be in the denominator, it has to be a perfect cube. So y times what? It gives you a y cubed. So this one you're going to multiply by the cube root of y squared. Okay, so we're going to multiply top and bottom by the cube root of y squared. So that means our numerator is now the cube root of x to the 4th y squared. And our denominator is 2z cube root of y cubed. Okay, so now remember, we can do the cube root of y cubed because it is a perfect cube. No way. So our numerator is the cube root. Notice in our numerator, we do have this x to the 4th, which we can simplify. So we know there in x to the 4th, there's one set of 3. with 1 left over. So we are x cube root of xy squared over 2z, and the cube root of y cubed is just y. Ta-da! Final answer. Last but not least, I want you to take a minute or two and try the example you try. Hopefully you find our final answer to be the square root of 35xy over 5y. And you made it to the end. Practice time.